Now here I provide a visual illustration of creating a caloric deficit through caloric restriction and why a caloric restriction, especially those who need significant weight loss, is the most practical approach versus creating a deficit just by exercise energy expenditure alone. Now we have to go back to the concept of calories or energy in representing the mass of fuel coming in, and the calories or energy expended representing the mass of fuel oxidized and subsequently exhausted in the form of CO2 and H2O. Now let's again use a container analogy. Just like a container full of sand as shown here, our body is essentially a container of mass. A good portion of the mass of this container is made up of sand, just like how a good portion of the mass of the body is made up of stored fuel molecules, fats, carbs, and proteins. Now at one point, you had two large scoopers of the same size, and I asked you to scoop as much sand into the container as you scoop out every day. No matter how many days of this you do, there will be no net change in the mass of the container. This is the same concept as you consuming the same amount of calories and thus fuel mass as you expend each day. There will be no net change in the fuel mass in your body, and thus the body mass does not change. Now let's say you wanted to reduce the mass of the container, but you still had to scoop in and out sand once each day. So you decide you wanted to achieve this by only increasing the amount of sand you scoop out. So you were given an extra scooper, but the scooper was really small, meaning you can only scoop out just a little bit more than you scoop in each day. Will the container mass decrease? Of course, since more is going out than going in. But will the mass of the container decrease at a high rate? No, since the net loss is very small each day. This means it will take a longer time for this container to reduce to the mass you want it to be. This is an example of a situation in which a caloric deficit is created by increasing exercise energy expenditure alone. Exercise energy expenditure is the extra small scooper. In this scenario, although a caloric deficit is established, it is a small one, and thus just a little bit more fuel mass is being expelled each day from your body than fuel mass consumed. The rate of weight loss will therefore be slow. Now, the more practical means of creating an energy deficit, as discussed earlier, is exemplified in this figure here. As you can see, for obese individuals, the resting energy expenditure, or basal metabolic rate, or BMR for short, is represented by this large scooper, which takes out most sand out of this container with each scoop. This means that there is a large amount of sand being scooped out each time, even without this little extra scooper. And so to reduce the mass of this container efficiently, it would make sense to just simply scoop less into the container. Now this illustration, although it seems overly simplistic, is how weight loss works. More mass going out than going in, and therefore, as a reminder, since calories are a proxy measure for fuel mass, we need more calories expended than consumed to create a deficit. And for obese individuals, since they have such high BMRs, reducing caloric intake, or caloric restriction in other words, would be the most practical approach to getting more fuel mass out of the body than fuel mass in. Now, as you can see highlighted here, this again does not mean exercise is irrelevant to weight loss efforts. So the question is, what is then the role of exercise? Now you will see it's all about changing our perspectives on exercise and its role in weight loss. A simplistic and more common perspective of exercise for weight loss is that it is how we burn extra calories, and this will help create a caloric deficit to drive weight loss. As we've emphasized before, for those needing significant weight loss, this is not a practical route, since the deficit created by just exercise alone would be relatively small. So the challenge is to not perceive exercise as a means to expend calories and to create a caloric deficit, but rather think of the long-term benefits of exercise and how that may help with weight control. What we will discuss in a few moments are the long-term adaptations to exercise, more specifically training, which is long-term exercise. And we will discuss how these long-term adaptations to training can promote healthy weight management or control. We will talk about things that the popular media does not talk about often, but the research is quite compelling. But first, let's tackle an important counter-argument that some of you may have. So when I say that the focus of exercise and weight loss should not be that it is a primary means of driving weight loss, some may counter back and ask, but can't you target specifically fat burning and therefore fat loss with exercise? For instance, some may say, well, okay, exercise may not contribute much to a caloric deficit, but it can target specifically fat burning and therefore fat loss can occur more effectively with exercise. Well, let's dive into this and introduce some counterarguments to this counterargument. Now, much of the contention surrounding this notion that exercise can facilitate specifically fat oxidation and therefore fat loss is the old concept of the fat burn zone. Now, we've all seen some rendition of this chart that we see here, whether it is at your gym or perhaps on a treadmill or an elliptical machine. And in this chart, we see something to the effect of the fat burning zone to be at intensities ranging from about 50 to 60% of one's heart rate max, so low to moderate intensity, steady state exercise. This is what most people consider quote unquote cardio. Now, this concept of the fat burn intensity zone is based on a huge misinterpretation of the science. The concept derives from the notion that at these low to moderate intensities, like 50 to 60% heart rate max, the rate of energy demand is slow, and thus your muscles can utilize a fuel source that is oxidized or burned, quote unquote, slowly for energy release. This fuel source are fatty acids, or simply fat. Now, this is factual. At lower intensities of exercise, there can be an increased reliance on fat for energy support. But what is misinterpreted is the difference between the per gram or the mass of fat being utilized versus the percentage of the total energy expended coming from fat. You see, at these intensities, the percentage of the total energy expenditure may come largely from fat, but this is a percentage of energy expenditure. What do you think is the rate of energy expenditure during steady state exercise at intensities between 50 to 60% heart rate max? It's pretty slow, and for a given time frame, not a lot of energy is expended, meaning not a lot of fuel is being oxidized, and therefore not a lot of fuel mass is being expelled from the body. So even though a large percentage of the energy expenditure is derived from fat oxidation, the actual mass or per gram amount of fat being oxidized and subsequently expelled in the form of CO2 and H2O is relatively small at these intensities of exercise. Meaning you are not exhausting a large amount of fuel mass, let alone fat mass, performing 50 to 60% heart rate max steady state exercise, at least within a typical time frame. So what do you think a typical time frame for the so-called quote unquote fat burn zone training is? Usually 30 to 60 minutes, right? Do you think with such a slow rate of energy expenditure, a significant amount of fat mass was oxidized and expelled during that 30 to 60 minute bout? No, not at all. The only way to utilize and expel a significant amount of fat mass during a bout of exercise in this intensity range is if your exercise bout is extremely prolonged, meaning many hours of exercise, an impractical time frame for exercise. Now let's take Michael Phelps here. In the peak of his training, he ate about 8,000 calories per day on average and consumed up to 10 times the amount of fuel, including fat, per day compared to the typical human. Now obviously he is very lean, but why? He often trains doing steady state exercise, so is it because he does so much training in this fat burn zone? This is absolutely not the case. It is because he trains for 5 to 6 hours per day, 6 times a week. He expends a lot of energy and therefore a lot of fuel mass, like fat mass, more than the typical person. So he eats that much per day and stays lean because he expends a lot of fuel every day due to his high volume of exercise, not because of this fat burning zone concept. So for the typical individual who exercises in this intensity zone for an hour 3 times a week, for example, there is not a significant amount of fuel, let alone fat fuel, being utilized and expelled from your body each time you exercise. So what are the practical implications here? Again, do not view exercise as a means to create an energy deficit or to drive fat loss specifically. This means don't get caught up in the concept of the fat burn zone training and doing quote unquote cardio all the time because you think that's the way to target fat loss. It is absolutely not. So yes, the so-called fat burn zone is overrated and based on a misunderstanding of the science. There is no magic with steady state exercise, and it is not an effective means to utilize and exhaust a significant per gram amount of fat unless of course you are exercising like this guy for a very prolonged period of time frequently throughout the weeks, which is impractical for most people. From a practical standpoint, if you only had 30 to 60 minutes per day, like say 3 times per week to exercise, go higher intensities. In fact, you could conceivably utilize and expel greater amount of fat mass doing higher intensities for 30 to 60 minutes versus doing 30 to 60 minutes of low intensity steady state exercise, or so-called fat burn zone intensities. Now, one question you should also understand is that even if your muscles are utilizing fat for energy support during exercise, are the fat molecules being used derived from fat stores in adipose? This is an important question since the whole idea of weight loss is to reduce the mass of adipose, which is largely attributable to the fat stores in adipose. Let's discuss. If you look at this figure here, you have energy expenditure rate on the y-axis and different exercise intensities on the x-axis. Now, as you can see here by the legend, the blue represents muscle glycogen or carbohydrates stored in muscle. The orange represents glucose, which is a free carbohydrate fuel molecule circulating in the blood. Turquoise here represents free fatty acids, which are fat molecules circulating in the blood, so not stored fat. And yellow represents fatty acids stored in different tissues, largely in the form of triacylglycerol or triglyceride, or TAGs for short. Now, TAGs can be found largely in adipose cells, but also in muscle and the liver, among other cells. Now, as you can see, for a given time frame of exercise, and that is an important concept, for a given time frame of exercise, so say like 60 minutes, as intensity of exercise increases, obviously the rate of energy expenditure increases as well. And as a percentage of the energy expenditure, you have less reliance on fat fuels, whether in the form of TAGs or free fatty acids, and greater reliance on carbohydrates in the form of glucose and mainly in the form of muscle glycogen. This is mainly because as intensity increases, the rate of energy expenditure also increases, and thus your muscles need to derive energy from a fuel source fast. Carbohydrates are oxidized and thus provide energy at a faster rate than fat. So thus, carbohydrates becomes a more reliable source of energy as intensity increases. Now you see here at 55% intensity, the percentage of the energy expenditure is largely derived from fat, both free fatty acids and also fat stores, triacylglycerols or TAGs. But as I said before, this is only a percentage and not a reflection of the total mass or per gram amount of fat actually being utilized. So because the energy expenditure is slow, the per gram amount of fat utilized is low for the given time frame of exercise. Now let's go back to the question we wanted to answer. The fat stores being utilized during exercise, regardless of intensity, is a majority coming from adipose tissue. Now, as you can see in the first bullet, the answer is no. Adipose fat stores are not an efficient source of fuel for active muscles during exercise. There are two explanations to this. First, If your active muscles are going to use fat as a fuel to help meet its energy needs, it will simply utilize the limited fat stores in said muscles. This is called localized fat stores. The muscle will use the fat stores that are already stored locally in the muscle. This is related to the second point. In order for active muscles to utilize fat stored in adipose, a lot of steps need to happen. First, the triacylglycerol molecules, the fat store molecules stored in adipose, must be catabolized or broken apart into individual fatty acids. This is called lipolysis. Then the free fatty acids need to circulate and somehow get to the active muscles. The muscle cells then need to actively uptake the free fatty acids. Then the free fatty acids can be oxidized for energy and converted to CO2 and H2O and subsequently expelled from the body. As you can see, this is a very inefficient route for fuel during exercise, which is a situation in which the muscles need fuel at an efficient rate. Thus, in summary, if your active muscles are going to utilize fat as a fuel source, it will likely use the more efficient sources, which include the fat already stored in the muscle or fat in the form of free fatty acids circulating in the blood. Point number 3 emphasizes again that muscles, like any other tissues/cells, will favor fuel sources that are immediately available, which are the fuel sources that are stored locally in the muscle. This primarily includes muscle glycogen and limited intramyocellular fat. Now, this fourth point is important. Although the percentage of energy expenditure derived from fat oxidation differs between low to high intensity exercise for a given time frame, let's say 60 minutes, the per gram amount of fat from adipose, or in other words, the adipose-derived fat mass that is being oxidized and expelled from the body, is pretty much similar across these exercise intensities, meaning there is negligible differences in the amount of fat from adipose being used as a fuel across these exercise intensities for a given time frame of exercise. Fat from adipose is simply not an efficient source of fuel for muscles during exercise. Thus, in summary, exercise is not to be perceived as a means to create a significant caloric deficit or to target fat utilization and fat loss, especially fat from adipose. Now, well, even with that said, some may say, well, what about fasted exercise, commonly referred to as fasted cardio, where one would usually in the morning exercise before eating anything? So you would be exercising in a fasted state or a post-absorptive state, meaning there are no nutrients actively being absorbed through the intestinal tract. In a fasted state, you are increasingly reliant on endogenous fuel stores like fat, since no quote-unquote new fuel is available. Now, the concept behind fasted exercise is that since the body is highly reliant on endogenous fuel stores during a fasted state, the additional fuel required during exercise would have to come from endogenous fuel stores as well. Well, it may immediately make sense, but what does the research have to say? Now, in this 2017 paper, the authors analyzed 5 individual studies that examined the effects of fasted exercise training. So in these studies, generally one group performed fasted exercise 4 to 6 times per week for 4 to 6 weeks, and the other group performed the same exercise but in a fed state. Now, when examining all these studies together, fasted exercise training yielded no changes in body mass compared to the fed exercise training. Now, the key aspect of these findings in culmination is that total daily caloric intake was controlled across the 2 treatment groups, meaning both groups in each study had similar caloric intakes. This suggests that the ultimate determinant of weight loss over time is indeed caloric intake, more specifically caloric deficit. In other words, if there is no caloric deficit, there will be no change in body mass, regardless of whether you do fasted cardio or not. So what other explanations are there to the ineffectiveness of fasted cardio compared to fed cardio? Well, as I said before, adipose fat stores is not an efficient fuel source for muscles during exercise, whether you are fasted or not. So there is really no adipose fat targeting by these methods, such as fasted cardio or any exercise method for that matter. Now, studies have shown, however, that there is increased overall fat oxidation rates during fasted cardio, but this does not translate to changes in body composition or body mass. If there is no caloric deficit based on physical law, there will be no mass deficit and thus no loss of body mass. So as I emphasized earlier, the benefits of exercise are not in its contributions to a caloric deficit or fat targeting. Exercise rather has long-term benefits to weight control through the adaptations to exercise training. Training again referring to long-term exercise. Now, as we all generally know, exercise is a stressor to the body. And if that stressor is consistently imposed on the body will adapt to the stressor so that the stressor eventually is no longer stressful to the body. For example, when we lift weights, over time we get stronger because we have adapted to the stress imposed by the load on our muscles. So what other types of adaptations occur in response to training? Well, as we know, exercise also imposes a metabolic stress, meaning it is a situation in which the body, particularly skeletal muscles, have an increase in energy and thus fuel demand. This is the general metabolic stressor. So over time, when this metabolic stress is continually imposed on the muscles start to adapt to it. It adapts in a way that makes it more efficient in meeting energy demands of exercise by increasing the efficiency by which fuels are taken up and subsequently oxidized for energy. This is why a particular exercise intensity becomes easier, quote unquote, as you train. So how does this adaptation to exercise affect weight control? First, you must understand that of all organs in the body, skeletal muscle is a major expender of energy and thus fuel even at rest, but especially during exercise since you need energy to contract muscles and muscles need to contract so that you can exercise. So if the muscles become more efficient at utilizing and oxidizing fuel, it affects the overall body's metabolism in that there is a shift away from fuel storage and towards utilization. This means these positive adaptations to exercise is anti-obesity or anti-obesogenic. So what are the specific adaptations that occur in muscle and what are the underlying mechanisms? So one mechanism I like to focus on is one that has a lot of research evidence. Adenosine monophosphate kinase, or AMPK, is an enzyme molecule that is found in almost all cells in the human body, including muscle cells. Now, you can think of AMPK as a metabolic switch. When AMPK is turned on for a long time, positive changes can occur in the muscle and vice versa when it's turned off. So what switches AMPK on? Well, research has shown that AMPK activation is increased with exercise, specifically because these factors related to exercise, muscle contractions, increased intracellular calcium, which is needed for muscle contractions, and increased AMP, which results from ATP usage, all occur during exercise and are stimuli for AMPK. Now, when AMPK is activated or quote unquote switched on, it is done so through a process called phosphorylation. And that is what this P icon represents. Now, I won't go into much detail about phosphorylation since that would sort of take us away from the main point here. Just know that this figure here, phosphorylated AMPK, represents activated AMPK. It is switched on. Again, due to exercise, more specifically, these factors that are related to exercise. These are the stimuli for AMPK activation. Now, when AMPK is switched on, it can in turn switch on other molecules, and we call these downstream targets of AMPK. One of the important downstream targets of AMPK is PGC1 alpha or PPAR gamma coactivator 1 alpha. Now, PGC1 alpha, when activated, can initiate epigenetic modifications, which again is a change in gene expression, not a change in your genetic makeup or genotype. In very, very simple terms, you can think of epigenetic modifications as you just switching on certain genes. And many of the genes that are switched on by PGC1 are those that regulate processes such as mitochondrial biogenesis, lipid or fat uptake and oxidation, glucose uptake, and anti-inflammation. So when these genes are switched on, in other words, when these epigenetic modifications occur, your muscles will have increased mitochondria, which improves aerobic fuel oxidation and energy support. It'll have increased lipid or fat uptake and oxidation, increased glucose uptake, glucose being a very important fuel source for muscle, and decrease in inflammatory molecules. Now, as you can see, all these effects, these specific effects of exercise through this AMPK PGC1 alpha mechanism are all in favor of long-term weight control and anti-obesity. These are the long-term benefits of exercise as it relates to weight loss or weight loss control. Now, we see that exercise has all these long-term benefits to the muscle, which can overall affect whole body fuel metabolism. But does exercise also affect other organs in the body that can also contribute to this anti-obesogenic effects of exercise? Now, the latest evidence in exercise physiology suggests that to be the case, and the positive effects of exercise on other organs is largely mediated through signals from the muscle. Let's explain. As you exercise and contract your muscles, the muscle cells increase synthesis and secretion of a variety of molecules collectively termed myokines. Myokines are essentially molecules that are synthesized by skeletal muscle and secreted into circulation. A list of myokines that are secreted with exercise is indicated here. Now, these myokines circulate and can interact with other cells in the body, such as those in adipose and the liver. These myokines have shown to exert positive effects on these cells, especially in adipose and the liver, and these effects can counter the effects of obesity or counter obesity in general. So some of these effects are highlighted here next to each of these organs, and also listed in more detail in the notes of your PowerPoint. Now, the specific effects of each myokine, as listed in your notes section of your PowerPoint slide, will not be asked on the exam, but may show up as a bonus question. Some of the effects of these myokines in adipose include decreased inflammation, decreased adipogenesis, which is the formation of adipose cells, increased lipolysis, which again is the breakdown or catabolism of fat stores like triglycerides, increased thermogenesis, which is an increase in energy expenditure by adipose cells, which is the opposite of energy storage or fuel storage, and increased insulin sensitivity, which we said in our initial lecture series was negatively affected by obesity. Now, all of these effects, as shown here, are collectively anti-obesogenic and is conducive to better weight control. Now, in the liver, we see effects such as increased gluconeogenesis, which is the formation of glucose, which is an important fuel molecule, increased insulin sensitivity, and increased beta oxidation, which is fat oxidation. Now, overall, exercise has long-term benefits to the whole body, not just in muscle. We also see that exercised muscles can communicate with other cells in the body to improve overall metabolic function that is anti-obesogenic and pro-weight control, and also pro-metabolic health. Now, one other aspect of these myokines is that the myokines can act on the cells that secreted them, the muscle cells, and it can exert similar positive effects that we see here on the muscle as well. Okay, so what else is there? What other long-term benefits does exercise exert on the body that is pro-weight control and pro-overall health? Well, let's talk more about this crosstalk or communication between muscle and adipose as we introduced in the prior slide. Now, one of the effects of long-term exercise that we see in adipose is referred to as adipose beiging, which was traditionally referred to as browning. Adipose cells can be generally separated into two types: white adipose cells and brown adipose cells. Then we have an intermediary adipose type called beige, which is essentially a white adipose cells that have shifted to be more characteristic of brown adipose. So what are the key differences between white and brown adipose, and why would beiging of white adipose be important to long-term weight control? Now, the key difference between white and brown adipose is the thermogenic properties. White adipose are not very thermogenic, meaning they have a low rate of fuel oxidation/utilization and thus low rate of energy expenditure. Therefore, white adipose cells are more conducive to energy or fuel storage, mainly in the form of fat store molecules, triacylglycerol or TAGs. One of the reasons why these white adipose cells are not very thermogenic is because they are not abundant in mitochondria, as shown in this figure here. Remember, mitochondria is where fuel oxidation and energy expenditure occurs. So because of this, the white adipose cells have a low capacity to oxidize fuel, and thus fuel storage is favored. Now, why are they white? Well, it's simply because these cells have large storage of fat, represented by this large yellowish circle referred to as a lipid droplet. Now, what about brown adipose cells? Well, these, as we said earlier, are more thermogenic than white adipose cells. Why? You may have already guessed that it is because they have more mitochondria, and thus fuel is efficiently oxidized and energy is readily expended, a portion of which is in the form of heat energy, hence the term thermogenic. This means brown adipose are less conducive to energy and thus fuel storage. This is why brown adipose cells are not very big, since they do not store fat or other fuels in large amounts compared to white adipose tissue. They are also brown because, one, they do not have an abundance of the whitish yellowing fat stores or lipid droplets, and two, mitochondria give off a darker brown color. So based on this information, wouldn't it be much more favorable for weight control if we had more brown adipose than white adipose? Of course, since again, brown adipose is not conducive to energy/fuel storage. But here is the thing. There is little to no evidence that complete shifting between these two adipose types can occur. But there is evidence that white adipose cells can become browner, but not really become entirely brown adipose types. We call these white adipose that have become browner beige adipose. Beige adipose are white adipose cells that have undergone the process of browning, or more appropriately termed beiging. So beige adipose cells are in between white and brown adipose, and they are more thermogenic with more mitochondria and thus less conducive to energy/fuel storage than white adipose. So yes, having your white adipose cells undergo this process of beiging would be favorable for long-term weight control success. So what really is beiging? It is mitochondrial biogenesis, the production of more mitochondria. That is what underpins this beiging effect. This is what causes the change in the color of white fat cells to become browner, or in other words, beige. So what causes beiging? There are two known environmental stimuli for adipose beiging. One being long-term cold exposure. Let me explain. When we are introduced to a cold environment that we are not acclimated to, how does our body respond to maintain our core body temperature? We shiver, right? We have rapid muscle contractions. Why? Well, because as we know, muscle contractions require energy, and thus our body forces shivering so that our muscles can oxidize fuel to expend energy. Some of the energy is used to contract the muscles, and some of the energy is released in the form of heat energy. This is a form of immediate thermoregulation during unaccustomed cold exposure. Now, what happens over time as you live in this cold environment? Do you continuously shiver every single day for the rest of your life? you eventually have less to no shiver response. So how does your body maintain its core body temperature in this cold environment? Well, one thing that happens is beiging or browning of adipose. The adipose cells become more thermogenic in response to long-term cold exposure, meaning they expend more energy and thus they generate more heat. So this beiging adaptation during long-term cold exposure is for the sake of thermal regulation to maintain core body temperature. Now, what is the second stimuli for adipose beiging? You guessed it, it's long-term exercise or exercise training. Research has shown exercise over time to elicit adipose beiging and thus make white adipose less energy/fuel storing and more fuel/energy expending, more thermogenic in other words. So what is the underlying mechanism connecting exercise to this adipose beiging effect? Now, as we introduced in the last slide, it is mediated largely through myokines that are again derived from muscle, especially muscle that undergoes frequent contractions during exercise. When we exercise, our contracting muscles can synthesize and release specific myokines that can interact with adipose cells and stimulate mitochondrial biogenesis and thus the process of beiging. The specific myokines that have shown to induce beiging are irisin, interleukin-6 or IL-6 for short, and meteorin-like protein precursor or MET-RNL. Now, other factors related to exercise that have shown to exert this beiging effect includes norepinephrine, which is one of the catecholamine hormones that are released during sympathetic activity like during exercise, fight or flight responses. So collectively, long-term exercise can promote weight control and protection against unhealthy weight gain through effects on adipose, making them less susceptible to fuel storage and more conducive to fuel utilization and energy expenditure.